Yeah, good evening, everyone. Today, so this is the session 3. So, first of all, I'll just recall some previous topics. Then I'll solve some sample problems. So at first, I'll recall what is the norm ball, just the definition. So, suppose there is this suppose x is a n-dimensional vector. So this is the n-dimensional vector. Then norm ball is defined as this. Suppose this is x is the mean of so the center of that norm ball. So then x norm of x minus xc, if it is less than equal to some r, then we can say that so this denotes a norm ball with center xc and radius r. So this is the definition of normal. So we can show that this is already professor has shown that this normal itself is a convex set. So then the next topic is what is the ellipsoid. So just definition. So x is also some n-dimensional vector here. So A inverse x is much less than equal to 1 if this, so where A is the matrix and x is a vector, then if this condition is satisfied, then we can say that this set of x is called the ellipsoid. And so yeah, after, so there is one application also professor has told for the ellipsoid. So suppose we have many, we have channels, some h is a vector, so we have channel h in a wireless communication. Suppose then uh, at the receiver, if we need to estimate h, so we'll estimate h hat. But how will you how will you determine that this h hat is estimated h hat is proper or correct or not? So that means if this distance between h minus h hat is low, then we'll say that this h hat is near to h actually. So this is the estimate is a true channel. So, but so this he has shown that so in an ellipsoid, suppose so this is the ellipsoid. Sorry, so this is the ellipsoid. Suppose this center is h hat, then h will be in this ellipsoid actually. So h will be somewhere here. So if the estimate is estimate is proper, or estimate is a true estimate, then this h hat will fall on h will fall on h hat. So our goal is to just this minimize the dimension of ellipsoid actually. So to estimate the to estimate h. So this is the application. Then in the next topic, what is a norm cone? So, so suppose this some x tilde is a vector which has which is dimension of n plus 1 cross 1. So first n vector is, suppose, so this is a vector. So this is also a vector, but this is the n dimensional vector, and another element is x n plus 1. This x n plus 1 is a scalar. So xn belongs to, so then the definition of norm cone is that, so suppose is a set of all such vectors such that this norm of this x tilde will be less than equal to xn plus 1. So this is the this is called the n plus 1 dimensional norm cone, and you can show that this is also a convex set. So then the next topic is what is polyhedron. So so similarly we can define here. So this if this x, suppose x is a vector, a is a matrix. So if ax less than equal to uh, so so before going to polyhedra we have two planes actually. One is in so intersection of hyperplanes. Another one is intersection of so first suppose the first one is half spaces. This is the hyperplane. So what will be the intersection of hyperplanes? So one can be shown in the equation promoted ax will be less than equal to some b vector. Okay, sorry, not vector. Sorry. Um, yeah, b vector only. Yes, and second one is for the hyperplanes cx. Suppose these two conditions are satisfied, then we can say that this is the polyhedron. Okay, so now one thing is that this suppose there are so I have shown that what is the LP norm. So LP norm is defined as was defined using this. Suppose there is a vector x, so LP norm will be this summation of, suppose this is the element is n dimensional vector, in mod of xi is the each element in x. So this is the definition. This was the definition of LP norm. So if I put p equals to 1, so here p greater than equal to 1. So if I put p equal to 1, then we will get what is the L1 norm, that is equal to same as I equals to 1 to n mod xi. So this is the L1 norm. So if I put p equal to 2, so I will get norm of x2 equals to I equals to 1 to n. So this is the L2 norm. So similarly, so now, so so now we need to find out what should be the L infinite norm. L infinite norm, I have told that L infinite norm can be written as max of y mod of xi. But how to show that using this formula? This is the formula. So how to show that? So suppose there is a norm p norm. So that is written as summation. So mod xi power p power 1 by p. Okay, so let's take power p. So that should be this only. Then that means mod of x1 plus mod of x2 plus mod of xn power, sorry, power p. Hmm. So now let us suppose assume that assume that the elements x1, x2, xn are ordered as so suppose x1 is the highest mod value, so we can so suppose there are n number of elements in the vector x, so we can order them in this order. Mod of x1 is more than mod of x2, and mod of x2 is more than mod of x3, and then dot dot dot. So the lowest element will be at the end, that is xn, mod of xn. So then we can write down that x of p power norm of, so norm LP norm of xp power, sorry, LP norm of x power p equals to so I have told that, so this is the x1. So in this figure, so this was the this thing. So then we can take common. Suppose we can take common of p. Okay, so it will be 1 plus then x2 by mod of x2 by x1 power p plus mod of. Plus dot 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 plus this mod of xn. Now here we have mentioned that this mod of x1 is more than mod of x2, and mod of x2 is more than mod of xn. So then we can write down that, so mod of x2 is so as mod of x1 is more, so it is less than 1, and mod of x3 by mod of x1, that is also less than 1. Okay, so everything is less than 1 here, even this last element also, mod of xn divided by mod of x1, that is also less than equal to 1. Less than 1. Hmm. So now as p tends to infinite, so now as p tends to infinite, as p tends to infinite, this power, so those these things are less than one, so this all will tend to zero. So then this will tend to, so all will be zero except this one, so it will be tend to mod of x1 power p. So that means norm of p will be same as norm of x1. Okay, so that means we can write down that, so this infinite norm will be mod of x1, that is max of I. Okay, this is the proof of infinite norm. And one more thing is that this norm ball actually. So so what should be the diagram of all three norm balls? That means L1 norm balls. So professor has already told that this L1 norm ball will be, suppose this is a unit radius norm ball. So that means mod of x1 will less than equal to 1 only. So that will, so suppose this is a two-dimensional plane. Okay. So suppose only two elements are there. Then here will be x1 and here x2. Then if you uh, so suppose mod of x1 equal to 1. So if you write down this mod of x1, mod of x equals to 1, that means mod of x1 plus mod of x2 equal to 1. So this is a so if you plot this x1 and x2 using this equation, then you will get this is tilted square. Okay, and this point will be 1 comma 0, and this will be uh, similarly minus 1 comma 0, and this 0 comma 1 and 1 comma 0. So this is the L1 norm ball, and what should be the L2 norm ball? So L2 norm ball will be, suppose this is the, so this will be 1 more less than 1. So that means if you put this so mod of x1 square plus mod of x2 square is less than equal to 1. So that means suppose this is the x1 x2, then this is the unit circle, so it will be, so it will be this is the L2 non ball. Okay, and what should be the L infinite non ball? L infinite non ball means this x of infinite equals to max of equal to 1. So that means then it will come around the square, actually proper square. Now we'll solve some problems, sample problems. So sample problems, suppose so first question is what was the matrix inversion lemma? So the question is this thing. This is 1 0 0 1 0 0 0 1. plus some so what will be the inverse of this matrix to see? So what will be the A inverse? So okay. So so first of all, let's write down the matrix inversion lemma plus T. So the lemma is this. Suppose A is a matrix A plus U C V inverse is equal to A inverse minus A inverse U C inverse plus B A inverse U inverse B A inverse. And if you put properly, then we can also write down that I plus some C D transpose, where C is C and D are two vectors. Then I plus C D transpose can be written as I minus this 1 plus D transpose C, and then it will be also C D transpose. Okay. Yeah, correct. So this was the formula, and we can do the inverse. So we can show that is this inversion is correct or not. So we can just multiply. So suppose I plus CD transpose. Sorry. Okay, I plus CD transpose multiplied with I minus CD transpose divided by 1 plus D transpose C. So that can be written as I minus CD transpose by 1 plus D transpose C, then minus, sorry, plus CD transpose minus CD transpose C D transpose C 1 plus D transpose C. It is same as, so this D transpose C is a scalar. Okay, so I minus CD transpose by 1 plus D transpose C plus CD transpose minus this is a scalar, so D transpose C can be written as outside of this uh, term. So then it will be uh, C D transpose C. So okay, 1 second. So C D transpose is this thing correct or not? So it will be C D transpose. Okay, so that means D transpose C is a scalar. So D transpose C, then C D transpose divided by 1 plus D transpose C. So now, so if you take these two things common, then it will be I plus CD transpose minus this thing 1 plus D transpose C, denominator and numerator is CD transpose 1 plus D transpose C, CD transpose into this is scalar is 1 plus D transpose C. So these two things then will be I plus CD transpose minus CD transpose that is equals to I. So if you you can see that if I multiply these two matrices, then it will give an identity matrix. So that means so this I plus CD transpose inverse can also be written as I minus CD transpose divided by 1 plus D transpose C. Okay, and so this matrix inversion is just by using the formula. Nothing is there. So suppose I is I3 here. So 1 0 0 0 1 0 0 0 1. Then this is the C, and this is also T. That is means D transpose. That means C transpose. Here this both C and D's are same actually. This plus so this 2 4 5. Okay, so 2 4 5 and 2 4 5. Okay, that can be written as so I. So this is the I minus CD transpose. That means multiplication of these two. Okay, so this means one matrix 4 4 8 10 divided by this D transpose C. So this is the 4 plus 16 plus 25. So it's 20 45. So it will be 1 minus 4 by 45. That means 45 minus 4, 41 by 45. So if you calculate properly, I may be so 45 by 45. So then so 0 minus 8 by 45, then minus 10 by 45 should be minus 8 by 45, and 1 minus 16 by 45, 45 minus 16. So maybe yeah, this is the inverted matrix, but you can check properly the calculation mistake or not. Okay, so then the next question is So the next question is I minus AB determinant determinant of I minus AB is same as determinant of I minus BA. So how to solve? So this is same. So now how to question? So determinant of I minus AB is so here let's take A comma B, both are some same dimensional matrix and square matrices. Okay, in cross n matrix. So now we need to show that how this I minus AB is same as I minus BA. So suppose let us take one uh, 2n cross 2n matrix. Okay, so here one is I n cross n, identity matrix of n cross n. Here also I n cross n. And here let's take A. Here let's take B. Okay, so let's take this. This is a common matrix of C. Okay. Now, what should be the determinant of C? So I have shown that in the last class that is determinant. Suppose C is a matrix. So what should the determinant of C? So to show that what should the determinant of C? So suppose we have to use this formula. Suppose a P is a matrix. P is equal to A, B, C, D, where A, B, C, and D all are matrices. But these are block matrices. Then what should be the determinant of P? So determinant of P is equal to date of A into date of D minus. So this is suppose this is the M cross N. So it should be N cross. Sorry. So it's a invertible cross M. It should be M cross N. Then it should be N cross M. It should be N cross N. So the dimension will be M plus N cross M plus N. So A inverse into C A inverse B. So if A is invertible and this can also be written as date of D into date of A minus B D inverse C. So if D is invertible. Now, if you see that here this A and D, so here this both A and D are identity matrices, so both are invertible. So we can use these two formulas together. These two formulas together we can use. So no, so this determinant of C can be written as first of all date of A. Date of A means identity matrix is determinant of identity matrix, that is 1. Then date of this D minus C A inverse. So D is the identity. So I minus. So C A inverse B. So C is a B actually. So B I inverse B I inverse A. That is the same as determinant of I minus B A. And using this formula only. Now, if I use the second formula, then I will get same 1 into determinant of I minus A I inverse B. That means determinant of I minus AB. So here it's so they are the determinant. So this is the 1, this is 2. So both are the determinant of same matrix, same matrix. So this then this determinant of I minus AB can be written as same as determinant of I minus BA. Okay. So now, so another question is that if so that means that if if I minus AB is 0, then I minus BA will also be 0. So if I minus AB is non-zero, that means I minus BA will also be non-zero. So that means so if I minus AB is invertible, then sorry, yeah, then I minus BA will also be invertible. And both in the both cases it will be true actually. So I mean the reverse version of this statement is also true. So that means and vice versa. So we can say one lemma as that if I minus AB is invertible, if and only if I minus BA is invertible. Okay, so this is shown using this determinant formula also. So this lemma can also be proved using alternative proof actually. So one alternative proof is some basic proof from the scratch level. Alternative proof is that. So that means if I show that if I minus AB is non invertible, that means if I minus AB is singular, then I minus BO will also be singular. So we can, if we show that I minus AB is singular, if and only if I minus BA is singular, we need to prove. So I minus AB is singular means determinant of I minus AB is equal to 0. Okay, if I minus AB is singular, so that means I didn't I minus AB is 0. So that means null. So there is so that means dimension of this null space of I minus AB is not equal to 0. That means the null space is can exist actually. So there is some non-zero vector. There exists some non-zero vector which is not equal to 0, such that I minus AB x will be 0. That means this ABX will be same as X. So if AB is X is same as X, then we can multiply B in both sides. So multiplying BX. Okay. So then you can write down. So now let this Y is another vector that is same as BX. Okay. Uh, so then we can write down. So BA minus I into Y equal to 0. Okay, but we so here this X is non-zero. Okay. So X is non-zero and this ABX equal to X. So suppose if X equal to 0, then ABX will also be 0. So one second, ABX equal to BX. Yes, yeah. So X is non-zero, so that means this Y is also non-zero. You can write down. So that means there exists some Y not equal to 0 such that BA minus I to Y will be 0. So Y belongs to null space of BA minus I. So dimension of null space of BA minus I will not equal to 0. So there will be at least one vector, non-zero vector. So that means this determinant of BA minus I will be 0. And then BA minus I will be singular. So hence it's proved. Then in the next question is that this rank of a matrix, rank of some matrix, some 2 cross 3 matrix. Let's take. Okay, so 1, 4, 5, 10, 4, 18, 26. So it's what should be rank of this matrix? So it's clear that rank should be less than equals to. So rank should be less than equal to. So rank of this matrix, so this A. Suppose rank of A will less than equal to 2 actually. Minimum of 2 comma 3. So it's 2. So rank of A is less than equal to 2. 2 less than equal to 2. Now we need to show that will it be 2 or less than 2. So here the two rows are there. So if you see that no, I mean the second row is not scalar multiplication of first row actually. So four, yeah. So these two rows are independent. R1 and R2 are independent, linearly independent. So rank is 2 actually, and you can check by using row reduced echelon form also. Okay, so rank of A equals to 2 and is equal to 2. Then so what should be the null space of? So suppose we need to find out. So uh, so then this is the R2 dimension, this is the R cube dimension. Okay, so here, so each column is from this R2. So suppose this is the range space of A. So this is the it's the rank is 2. That means the dimension of range space is already 2. So this null space of A transpose is so there is no basis remaining in R2 for the null space of A transpose. So that means this whole thing will be covered by range space of A, and null space of A transpose will only be null set. And this for this case it should be the range space of A transpose, and here null space of A which has only one, because the dimension is 2, here the dimension will be 1. Okay, so only one basis is there for the null space of A. So we need to find out. So next question is find the basis for null space of A. So the solution is that, so we need to find out the null space of A basis. Okay, so this means Ax equal to 0, and then we need to show that we need to find out this x. So suppose x A is the 145, 145, and then 4, 18, 26. So the equation will come like this: x1 plus 4 x2 plus 5 x3 equal to 0, and this is the one equation, and this 4x1 plus 18x2, 4x1 plus 18x2 plus this 26x3. And as these two rows are linearly independent, this one and this one are linearly independent, so that means these two equations are different, I mean they are not same. So I mean, so these two equations are not are unique I mean are different equations. So if there is one more different equation, then we can find out x1 x2 x3 from the three equations, but here only three unknowns and two equations. Now we okay, now let's take x1 equals to some 1. Okay, then we can solve x2 and x3 and put those x1 x2 x3 in that in a vector, then we'll get that vector as a basis of null space of A, and then find the solution for x2 using 2. Okay, so here suppose x1 is 1, then what should be the x2? So 4x2 plus 5x3 equals to minus 1. 18x2 plus 26x3 minus 4. So 3 and 4. I'm getting this x3 as 1 by 7, but please you can check here if this is correct or not. And then x2 is minus 1 minus 5 x3 by 4. So x2 is minus 1 minus 5 3 by 4. Okay, so then it should be minus 7 minus 12 28. So now the basis will be this 1 minus 3 by 7 and then minus 5 by 7 is 1. The basis is not unique, so is one basis for null space of A by 7. Oh, sorry, this is 1 by 7 only. Okay, you can check it, it's correct or not. Okay, so then the next question is question number 4. No, so 5, 6. 6, the question is that ax1 plus bx2 less than equal to c. So the questions are is this a convex of base? B is a concave cone. C is a convex affine. D is concave. hyperplane. Solution is it's just a one line, just need to check. So here this a x1 plus, so let's take this a and b as a vector, okay, and this is the x1 and x2 is another vector that is equal, that is less than equal to c, we can write down. So these are some c, sorry, some x, some b vector, the x vector. So you can write down, so d transpose x less than equal to c. So this is the hub space, you know. This is the convex hub space. Then the second question is, so suppose there is a matrix, some 10, 11, 12, 13, and the x1, the norm is less than equal to x1 plus x2. So the option A it's a hub space. Okay, so this is a convex set also. This is a convex set, convex subspace. So you can check that is a convex set or not. So you can take some t belongs to 0, comma 1 and then check that c into x plus, sorry, that t into x plus 1 minus t into a y some other vector that will also fall on that space. So this is a convex set also. So then okay, so here the second option is convex cone. She is hyperplane, is ellipsoid. So we have the definition of all these hub space, convex cone, hyperplane also. So you can go to there. Okay. So, ellipsoid is this a into x is less than equal to some uh, one norm of this. Okay. Then what will be the norm cone? So convex cone will be this. Mm, so this is less than equal to some element xn plus 1. Okay. So from the definition itself, it's a convex cone actually. So it's a convex cone. The next question. Okay. So which is more, L1 norm or L2 norm? Okay. So suppose L1 norm is this. Suppose there are two elements here in this case. Okay. Suppose x belongs to R2. So then, so it will be easier to prove here. And this is the L2 norm. Going to show that which is bigger from this equation, from these two now. Okay, 1 and 2. So if you square each norm, it will be x1 plus x2 mod square. So that means mod of x1 square plus 2 mod of x1 x2 plus mod of x2 square. That is same as x1 square plus x2 square plus 2 mod of x1 x2. And this second one is x2 norm. So x2 norm square is equals to x1 square plus x2 square, and this is the mod element, so this is greater than equal to 0. So obviously the first one is more than the second one. Square is more than equal to, as this. Okay, so then this x1 norm is more than equal to this x2 norm. So L1 norm is more than L2 norm. Okay, so this that's all for the problem questions. Okay, this the problem questions. You can ask me if there is any doubt. After that, I will just introduce one more mathematical topic, that is SBD, singular decomposition, that will maybe required later. So that's why just theorem only. So up to this, if you have any doubt, you can ask me. So you can revise. So first I revise this: what is norm ball, ellipsoid, and then what is norm cone and polyhedron. Uh, then also I have proved here that this what, so I have shown the different diagrams here. So yeah, second. So where do you share this lecture notes? Yeah, actually, I have in the chat box, I have posted a link. I had posted a link last day. So if you click on that link, that will open one. Okay. So yeah, if you click that link, then you will go to one folder. There, this all the lecture notes are uploaded, and in that Excel sheet also the YouTube video link also uploaded. So you can find there. Okay, I'll send the link again here. Okay, let me share it now. Yeah, I send the link again. Okay, so any reference book. So if you go to professor's page in the NPTEL, there maybe you can find any reference books actually. Okay. Actually, I don't know what should be the proper reference book for this wireless big data as well as machine learning optimization problem. So I know only some general optimization book actually. So, but professor will suggest better. So you can check it from the NPTEL website. Okay. Okay. If you don't have any question up to this, then I can start one more topic, that is just introduction of another topic that will be useful in this community. Okay, so let me revise again. So this LP. So first, if I put the p equals to 1, then that this will give L1 norm, and p equals to 2, then that will give L2 norm. And if p is infinite, then that will give infinite norm. So I have shown that infinite norm can be taken as maximum of all the absolute value of all the elements in a vector, and the L1 norm ball can be shown as a tilted square. Uh, So it's I have shown here in the two-dimensional space, but in the n-dimensional space, uh, the nature of the diagram will also be same. So for L2 norm, for L2 norm, it will be a circle, but in the n-dimensional space, it may become one sphere n-dimensional. Okay, and L infinite norm ball is a square matrix, proper square matrix. Sorry, proper square in the two-dimensional space. So these are the problems, sample problems. So first of all, this I have shown how to find out the inverse of I plus CD transpose. It's just using the equation. Okay, and this was the matrix inversion lemma. So I have used this lemma to find out the inversion of a matrix I plus CD transpose, and that is can be take the inversion of I plus CD transpose is equal to I minus CD transpose 1 divided by 1 plus D transpose C. Um, then so then you can put those C and D in this equation, and you can find out what should be the inversion of the matrix. Then the second problem, I have shown that this I minus AB, determinant of I minus AB is shown as can be taken same as determinant of I minus BA, which is proved by using this matrix determinant lemma or theorem. So actually, this theorem I didn't prove. Actually, I have used this theorem. Uh, Okay, so I can show it here. So one way I can show it here. Suppose there is determinant A, B, C, D. Okay, so we need to find out the determinant of this matrix, where A is also a matrix, C is also a matrix, D is also a matrix, and now we know. So let A inverse exist. That means A is invertible. Okay, so then A, B, C, and D can be written as. Okay, I, and this is okay, this is 0, and so then it should be A, and it will be anything. So A, and then for the second element it will be so it's 0 I A, and then it will be second element will be uh, this and this, then it will be A, and 0. So C. So it will be C A inverse, and then uh, C A inverse, and then it will be I. So it will be B actually for this case. B is equal to I A, then this fixed C A inverse A, 3A inverse into something C plus this D. So mm, so let us take this element as D minus, sorry, D minus C A inverse B. Then so it will be B is equal to, so it will be B actually. So B C correct, and then C inverse B. Then B minus C, correct only. So you can multiply these both matrices, and you can show that this right hand side is same as the left hand side. Then determinant of this right hand side will be same as determinant of left hand side. So determinant of this A B C D will be same as determinant of this thing and determinant of this thing. Okay, and then determinant of this lower triangular matrix is same as this determinant of these blocks, and here also upper triangular is same as determinant of these blocks. So that means determinant of I into determinant of I for this case, and here it will be determinant of A into determinant of D minus C A inverse B. Okay, this element. So that means this is same as determinant of A into determinant of D minus C A inverse B. Okay, so that's what I have written in this formula, same formula. Okay, and similarly, you can write down the same matrix in form of some other way. So there you can show that this thing is, this thing holds true, and then then by that way I have shown that this determinant of I minus AB is same as determinant of I minus BA. And here is one basic level proof that if I minus AB is invertible, then I minus BA will also be invertible. And I have shown that what should be the rank. So it's just to find out the rank of this matrix, because this kind of questions may come in the assignment. So rank of one matrix can be less than equal to the dimension of that matrix. So here this that will be more less than equal to 2 comma 3, but we need to check that is there any linearly dependent rows or columns there or not. So here there is no linearly independent row. So that's why here the rank will be 2, full rank matrix. Then so here the rank is 2, and in the 3 R cube space, so this range space of A transpose, that is the column, sorry, row space. So row space dimension is 2 only, as the rank is 2. But so null space will have only one basis or one dimension. That means this 3 minus 2, that is 1. So that's why. Then I have shown that how to find out the basis of null space by using the equation Ax equal to 0. And here there are some short questions on the convex half space. So Ax1 plus Bx1 is less than equal to C, all are scalars. So now we can show that this D transpose X is less than equal to C. So that is the equation of convex half space. And this one matrix is there. So some matrix less than some matrix into some vector norm of that case, norm of that term matrix multiplied with a vector is less than equal to some element. So that is the equation of convex cone. And then I have shown that which is more, L1 norm or L2 norm. So for the two-dimensional case, I have shown that L1 norm is more than L2 norm. If you extend the to n-dimensional space, in that case also it will be more than L1 norm will be more than L2 norm. So that's all. And then I'll write down one theorem, that is the for the singular value decomposition. So this may be helpful in wireless communication or any other machine learning algorithm, singular value decomposition. Composition. I'll just write down the theorem here. So suppose there is a matrix, a square, sorry, a rectangular matrix, any matrix. Okay, so matrix can be rectangular or square. So a rectangular matrix. Let's generalize this. Okay, our last day I have written for the similarity matrix some square matrix. Okay, A m cross n. So that is not true actually. Similarity matrix exists only for square matrix. Okay, so can you please change that to rectangular to square matrix in the last class where I taught the similarity transform. So here the rectangular, suppose let's take a rectangular matrix. This is the generalized version of decomposition. So for a rectangular matrix, some uh, okay, some M cross N matrix. Okay, okay, rectangular matrix belongs to okay, um, and comma A. So suppose A is the matrix, so that belongs to Rm cross N. So then and sigma 1, sigma 2, sigma R. Oh, sorry. So and rank of A is same as R. Okay, and sigma 1, sigma 2, sigma R are the singular values for A. So what is the singular values? So singular values means mm, suppose so singular values means A admission A. So equals to square root of eigenvalue of Hermitian A. Okay, so this can be applicable for complex matrix also. So this is the singular values. So and also assume that sigma one, these sigmas are ordered. So ordered means this sigma is more than equal to sigma two, that is more than equal to sigma three, that is more than equal to sigma, all are greater than zero, because this square root, so positive values actually. So okay, and this and then okay. Okay, so then A can be, then we can write as some unitary matrix Hermitian A B is equal to, and this is a diagonal matrix. What should be these the diagonal elements? I will show, but this is the these are the unitary matrices. So this is not diagonal. So the this thing, these are matrix. I'll show what is the sigma here. So okay, so sigma structure is like this actually. Sigma structure is some D R cross R, zero, all others are zeros. Okay, so that means what is the D? D is a diagonal matrix. So D R cross R is a diagonal matrix. That means the diagonal sigma 1, sigma 2, dot sigma R, all are zeros. And so sigma can be constructed. So capital this sigma. So this sigma can be constructed using D matrix. And D is the diagonal elements of sigma 1 diagonal matrix, where the diagonal elements are the singular values of that matrix A. Okay. Mm. So this is the theorem. So that means we can write down for any matrix U Hermitian A U is equal to some sigma. Sigma is diagonal matrix. So this then sorry this is the P. So then A can be written as U sigma B Hermitian. Okay. So this is the SBD, signal value decomposition theorem. So this is the helpful theorem which will be applicable in every domain. So there is one application in wireless communication. So one application is that, so there are lots of applications, infinite number of applications. So one application. So in OFDM, so there is one modulation scheme in wireless that is applicable for one kind of channel, that is frequency selective channel. So the suppose there is a modulation scheme that is named as OFDM, orthogonal frequency division modulation. It's just a name. So in this case, in the OFDM case, the so if I transmit data, after that some portion of data again actually, so that will give so that will make the channel as a circulant channel actually. So circulant matrix is nothing but another matrix. So some circulant matrix will come actually here in this case, circulant matrix. So that means some y equal to some hx plus w, where y is the received signal, h is the this circulant matrix actually. So circulant matrix, this is the overall idea actually, not the exact thing. Circulant matrix, and x is the transmitted symbol vector. So our job is to estimate this x actually using this y, and this w is the noise. So additive noise at the receiver. So this is the symbol vector. So now this circular matrix. So this is a circular matrix. So if you do SVD of a circular matrix, you can write down. So you can decompose that H using this SVD. Then you will get one this diagonal matrix, that is sigma. So that will diagonalize this channel actually. So if the channel is so if this matrix is circulant, then we can then we can write after some multiplication of transform matrices actually at the transmitter receiver matrices that and each element can be written as. So suppose this is a y, so this is some diagonal matrix. This is the y tilde, so this is the x plus some noise. Okay. So this diagonal means y1 can be written as something constant, uh, some h1 into x1, y2 tilde can be written as h2 into x2 plus noise actually. So this is called the parallel, parallel channels. So I mean here this finding this x will be difficult, but here using this uh, parallel channels we can find out x1 x2 each element individually with less complexity actually, only one. So x1 is dependent on only this equation and x2 is only this equation, so we can find out x1 x2 easily here. So this is the one application in this wireless communication. Okay, so I think one has some doubt. Yeah, YouTube link. Yeah, then yeah, I'll send the YouTube link in the chat also. Okay. Okay, so that's all for the day. You can ask me anything here. Okay, I will wait for 5 more minutes, then we can leave. Okay, thank you for joining. Think